In contrast to valence bond theory, which assigns bonding orbitals to individual atoms, molecular orbital theory assigns the orbitals involved in bonding to the entire molecule. The simplest illustration of molecular orbital theory can be seen with the hydrogen molecule. According to molecular orbital theory, the 1s atomic orbitals of the two hydrogen atoms combine to give two molecular orbitals. Because atomic orbitals are wave functions, they can combine either constructively or destructively. Additive or constructive combination of the two atomic orbitals gives a bonding molecular orbital, while subtractive or destructive combination of the two atomic orbitals gives an anti-bonding molecular orbital. The bonding and anti-bonding molecular orbitals formed by the combination of two 1s orbitals are called sigma 1s and sigma star 1s respectively. The bonding molecular orbital, sigma 1s, is lower in energy than the original atomic orbitals. And the anti-bonding molecular orbital, sigma star 1s, is higher in energy than the original atomic orbitals. Like atomic orbitals, molecular orbitals can accommodate a maximum of 2 electrons each, with the electrons in the ground state occupying the lowest possible energy orbitals. The molecular orbitals in the hydrogen molecule can be represented with lines or boxes placed at the appropriate relative energy levels. The 2 electrons in the hydrogen molecule both occupy the bonding molecular orbital. Because most of the sigma 1s bonding molecular orbital is located between the two nuclei, electrons in this orbital draw the two nuclei together by electrostatic attraction. The sigma star 1s anti-bonding molecular orbital consists of 2 lobes. The majority of the space occupied by the 2 lobes does not lie between the two nuclei. In this molecular orbital, the region between the 2 lobes is known as a node. Electrons in this orbital would actually draw the 2 nuclei apart by electrostatic forces. Hydrogen has no electrons in this anti-bonding molecular orbital. We can use the relative numbers of electrons in bonding and anti-bonding orbitals to determine the bond order. Bond order indicates the strength of the bond and is equal to the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals divided by 2. The hydrogen molecule has 2 electrons in its bonding molecular orbital and has no electrons in the anti-bonding molecular orbital. Therefore, its bond order is 1. Imagine describing a diatomic helium molecule using molecular orbital theory. Diatomic helium would have a total of 4 electrons. The first 2 would occupy the sigma 1s bonding molecular orbital. The third and fourth electrons would occupy the sigma star 1s anti-bonding molecular orbital, which is the lowest energy molecular orbital available. Diatomic helium would have 2 electrons in a bonding orbital and 2 electrons in an anti-bonding orbital, giving it a bond order of 0. Molecular orbital theory predicts that a molecule with bond order 0 will not exist. This prediction is supported by the fact that there is no such thing as a diatomic helium molecule.